So today I will tell you about the complexity of the surjective constraint satisfaction problem. Thank you for coming. This is my first talk in the internet. Let's see how it will go. So I will start with the definition of the constraint satisfaction problem. So constraint satisfaction problem is a very general problem in computer science. Every time you have some constraints, it's a constraint satisfaction problem. And I don't want to waste your time explaining why this is really important problem. I just want to cite Andrei Bulatov, if you know him. And usually in his talk, he explains why every problem or almost every problem is a constraint satisfaction problem. Like every problem we solve in our real life is a constraint satisfaction problem. So anyway, constraint satisfaction problem is very general and very important. I want my talk to be on elementary level. So I will give you a lot of examples just to give you some intuition. I'm not sure whether you are familiar with the topic. And the first example is like this. If we consider two-element domain, and on this two-element domain, we have just one predicate inequality, then constraint satisfaction problem can be viewed, and the instance, an instance of this constraint satisfaction problem can be viewed as a graph. So you have a graph, and variables are vertices, and your constraints are just edges. Yeah? And if you have just two elements in our domain, it's just the problem of graph two coloring. So we need to color a graph into two colors so that adjacent vertices have different colors. For example, if we have this graph, we can try to color, and so we get a contradiction. And since we get a contradiction, it means that we have an odd cycle. And so every time we try to color, either we can color the whole graph or we will find an odd cycle. So this problem is easy to solve, which means that for this constraint language, the problem can be solved in polynomial time, so it's easy. Okay, let's consider a different problem. If we have three colors, so the same constraint language, just one predicate in it, and we have three elements in our domain. So we want to color a graph into three colors. And in this case, if we start coloring, we can do it like this, like this, like this. So again, we get a contradiction. So we can check that this graph cannot be colored into three colors. So this instance has no solutions. The problem is that we don't know polynomial algorithm on how to solve this constraint satisfaction problem and how to color a graph into three colors. So this problem isn't P-complete. That's what we can prove. Give me a second. Okay, next example. If you consider a system of linear equations, what it means. For example, here we have three elements in our domain. It's 0, 1, 2. And in our constraint language, we have just equations with just three variables. Then constraint satisfaction problem over this language is just system of linear equations. And what we know? We know that Gaussian elimination can solve this problem, and we know that this procedure is efficient. So we can efficiently solve this problem. And this means that this problem is easy, so it's solvable in polynomial time. So again, for this constraint language, constraint satisfaction problem is easy. The next example. Sorry that I have too many probably. Anyway, the next example. If we have two elements in our domain and we have three predicates in our constraint language, equality, and also two unary constant relations. So we can mark some variables that they are red or they are blue. Okay, for example, in this instance, if we try to find a solution, we get a contradiction because here we have equality, but one variable is red and another is blue. So this instance has no solutions, and it's clear that the instance has a solution if and only if we cannot connect red and blue vertices. Okay. And so this problem is also easy. It can be solved in polynomial time. We can easily check whether there is path between two vertices, red and blue. Okay. Now I want to repeat the formal definition of constraint satisfaction problem. So today I consider only constraint satisfaction problem on a finite set. So let A be a finite set. and let gamma be a set of relations on a set A. This gamma we call a constraint language. And then for every constraint language, we have a decision problem given a conjunction of predicates where all the predicates are from gamma. And we need to decide whether this formula has a solution, whether this formula is satisfiable. So for different constraint languages, we have different decision problem and we have different complexity. And as we saw from the examples, sometimes this problem is easy, sometimes this problem is difficult. And yeah, please interrupt me if you have any questions. But
so let me check. So for every variable, you have the same domain, and for every set of variables, there are the same number of allowed constraints.
Yes, like usually in a general setting, every variable can have their own domain, but here we assume that all the variables have the same domain, because this is almost as general as the general question, yeah.
And technically, probably you also allow using the same variable twice in one constraint.
Yeah, that's for sure, yeah. So I just use relations from our constraint language, but I can use every variable as many times as I want. Just another example, if we are on 3-element domain and in our constraint language we have two predicates, x less than y and x less than or equal to y, then for example, this instance obviously has no solutions. And this instance has a solution, for example, 0, 0, 0. I think it's clear, yeah? So for different constraint languages, we have different decision problems and we study the complexity of this problem. And in 2017, we proved that this problem is either solvable in polynomial time or this problem is NP-complete. And now we have an easy characterization. Today, I don't want to explain what polymorphism is because I realize that it's not so easy probably. But anyway, the point is that it's really easy criterion when constraint satisfaction problem over gamma is easy and when it's NP-complete. Okay, so for constraint satisfaction problem, we know everything. And now let's go to the topic of my talk, surjective constraint satisfaction problem. Here, everything is the same. Again, we have a finite set A, and we have some set of relations gamma, which is a constraint language. And for every gamma, we consider decision problem, surjective CSP over gamma. Again, I have a conjunction of predicates where all the predicates are from gamma. But this time we need to decide whether this formula has a surjective solution, which means that any element from A should appear in the solution. Example, if we are on a 3-element domain and we have just one predicate x less than or equal to y, then for example, this instance has a surjective solution, for example, like this, 0, 1, 2, 2. Definitely it's a surjective solution because 0 and 1 and 2 appears in the solution. But for example, this instance, it has a solution, for example, 0, 0, 0. But this instance doesn't have a surjective solution because all the variables should be equal. So no surjective solutions. And so the main question I'm asking today is what is the complexity of the surjective constraint satisfaction problem?
So you just add one non-local constraint, which is surjectivity,
yeah,
and correct. See how it changes things. And why, can you say maybe some words why this surjectivity is, theoretically you can probably add different local global constraints. Why it's natural or best, most interesting one.
Okay, I will give you some examples. So I will try to advertise this problem today. Yes, I will show you some examples to convince you. But first, I want to show you two simple examples, and probably they're also natural. And yeah, and the first example is like this. Again, if you consider 3-element domain, and we have just one predicate equality in the constraint language, then again, any instance can be viewed as a graph. Yeah. And for example, this graph has just two connected components. So it can be colored into 2 colors, but it cannot be colored into 3 colors. So it means that this instance has no surjective solution. Yeah, and also it's clear that this problem is easy. Yeah, Because every time you have just one equality predicate in your constraint language, you just need to count the number of connected components and compare this number with your with the size of your domain. So this problem is easy. And one more example of surjective constraint satisfaction problem, which is actually harder than usual constraint satisfaction problem over the same constraint language. If we are on 3-element domain again, and we have just one predicate, x is not equal to y plus 1. Here, y plus 1 is modulo 3. Okay, what is clear? It's clear that this instance has a solution 0, 0, 0. So it has a trivial solution 0, 0, 0. But let's check whether it has a surjective solution. So let's put some color to x6. Then we can calculate that all the remaining variables should be either blue or red. So they're either 0 or 1s. So this already means that this instance has no surjective solutions. Okay? And we can even check that if one of the vertices is red, then all of them, if one of the vertices is blue, then all of them are blue. Anyway, the point is that this instance has no surjective solution. And we can actually prove that this problem is NP-complete. So you see that CSP over this constraint language is easy and actually trivial because 0, 0, 0 is always a solution. We don't need to solve anything. We can always return, yes, there is a solution. It's solvable. But for surjective CSP, it's not easy and it's actually NP-complete. Okay. So let's compare what we know about CSP and surjective CSP. The complexity of CSP is known for all gamma. By known, I mean that we know whether it's tractable, so solvable in polynomial time, and NP-complete. The complexity of surjective CSP is widely open. And this is really amazing because for surjective constraint satisfaction problem, we have very simple constraint languages with unknown complexity. And for example, constraint satisfaction problem was an open, like the complexity of CSP was an open question for many years, but for many years, we did not have any good example, any good constraint language with unknown complexity. So all examples were artificial. And here we actually have simple examples, simple constraint language with unknown complexity, which is amazing in my opinion. What else is clear? It's clear that CSP can be reduced, can be polynomially reduced to surjective CSP. And this reduction is really trivial because if you have a CSP instance, then you just add the variables you never use. And using these variables, you can always achieve surjectivity. Yeah? So any instance of CSP can be viewed as an instance of surjective CSP. And any solution can be made surjective. That's the reduction. As we know from the previous slide, I did not prove it, but it's quite easy that sometimes surjective CSP is harder than CSP over the same language.
But if it's quite easy, maybe you can say, just say the proof. Why this it's NP-complete, this one example which you showed, or not so easy.
Okay, in few slides, I will show you another example, which is also NP-complete, and it's more beautiful than the one I showed you before. So let's consider the next one. Okay, another simple and even trivial reduction is like this. Surjective CSP can be reduced to CSP over the same language, but here we need all constant relations. And this reduction, this is a Turing reduction, and this is really simple reduction. I will explain how it works. Assume that we have elements A1 and so on AS in our domain. So first we just guess as variables taking these values, A1 and so on AS. We add these constraints, and then we solve the instance over gamma with all these constant relations. So what we actually do, first we just guess variables taking all different values from the domain, and then we just solve CSP. it's clear that we have only polynomially many guesses for the variables because our domain A is fixed. And that's how this Turing reduction works.
Oh, so your gamma, the size of the alphabet is just part of the input polynomial. So if you can add or try all the, yeah.
Gamma is not part of the input. Gamma is fixed.
Yeah. And alphabet is also fixed, so you don't care whether the polynomial is of this degree or whatever.
Yeah, that's true. That's true. I don't care about the degree.
That's why it's obvious.
Yeah, I'm not saying that it's a good reduction or fast reduction, but today I only care whether the problem is polynomial or NP-hard. So for me, and I consider only case when A is fixed. So I can always do this reduction. Okay, so we have this reduction. And actually Hubi-Chen conjectured that we can also make the backward reduction. So he conjectured that surjective CSP and CSP over gamma with constant relations always have the same complexity. And this would be really amazing because this would give us very simple characterization of the complexity of surjective CSP. We just need to add constants and then we know everything. Yeah. And for example, for two-element domain, this conjecture holds. So we know that surjective CSP over some constraint language on a two-element domain is always equivalent to CSP. Okay, so that's what we have and what we know about CSP and surjective CSP. Let's go on. Again, I want to advertise this problem. I will try to convince you that it's really natural and beautiful. So let's consider graph homomorphism problem. Probably you know what it is, but I will repeat. Suppose we have, I hope I don't see what you see, some part is covered. Anyway, suppose we have a finite graph H. Then I consider decision problem, homomorphism of H, which is also called H coloring problem, which is like this. Given a graph G, and I need to decide whether there exists a homomorphism from G to H.
The size of H is fixed, and we allow the polynomial to be, or degree could depend on H, on the size of H.
Yeah. Here H is fixed. So for every H, I have a decision problem. And as an input, I get a graph G, and I need to decide whether there exists a homomorphism from G to H. So I map vertices to vertices, and I want edges go to edges. Okay, I think it's clear what homomorphism of two graphs is. Yeah,
so it's a special case of CSP.
Yeah, and this is a special case of CSP, and I just wanted to explain this. Probably it's really clear.
Sorry, for me it's not clear what means homomorphism of graphs.
Okay.
If there was an edge on the left, there is a corresponding edge on the right.
Yeah, that's true. So it's a mapping from vertices to vertices, and if we have an edge in the left, then we have an edge in the right.
Now I do not understand it. You say if, or you say if and only if?
If. I say if.
Okay. And
it's not isomorphism, it's homomorphism, yeah.
Okay. And you do not require that this mapping is surjective?
Yeah, I do not require this mapping to be surjective.
Okay.
CSP.
Yeah. You're right. So anyway, here it's clear that this homomorphism.
Sorry. So if two nodes go to the same node at the right, must they have an edge or not?
If H has a cycle or has loop, then it's allowed if they are neighbors. But if H doesn't have loops, this means that different neighbors cannot go to one edge.
Yeah, that's true. So if in the right-hand side we don't have loops, then we cannot like identify two variables, like two connected variables. Yeah, two adjacent variables. Yeah. So it's clear to see that this problem is just constraint satisfaction problem, just variant of constraint satisfaction problem, because vertices of graph G can be viewed as variables, and edges of graph G can be viewed as constraints. Yeah, and so this problem is just constraint satisfaction problem over a language having just one binary relation. This relation is actually this graph H. So the domain is just the set of vertices of graph H. Yeah, and the only constant relation we have is the relation corresponding to the graph H.
Yeah,
Okay.
I think it's really obvious if you make some pause to let Bruno
Okay.
See this, and then we can continue, I guess.
Yeah. Okay. And
so, Bruno, is it clear or not? What he's.
So what I'm saying here, I'm saying that graph homomorphism problem between G and H is equivalent to graph 3 coloring. So imagine we want to map graph G to graph H, which means that we want to assign a color to every vertex in the left-hand side. And what we also want, we want adjacent vertices to map to adjacent vertices in the right-hand side, which means that they should be of different color because we don't have loops.
Okay, okay.
So actually,
something is confusing. If just say if it's something is confusing, it's we should not run too fast if something is not clear.
I think it seems okay to me.
So every vertex on the left is a variable, and if a variable has a value which is a vertex of the right, it's just a part of the homomorphism. And so we look for the values for all variables, and the constraints are essentially constraints on local constraints on pairs of variables. So everything seems to be quite nothing dangerous, I guess.
yes.
Okay.
Okay. And the next slide is almost the same. But here I added one word, surjective homomorphism. So this time I want this mapping to be surjective. And again, you can see that if I added this word surjective in the definition of homomorphism problem, then I add surjective in the bottom. So surjective homomorphism problem is equivalent to surjective CSP over the constant language having just one binary relation corresponding to H. And this problem, I think, is very natural. So we are asking whether there is a surjective homomorphism from one graph to another graph. Okay, is it clear? I guess nothing new on this slide. Yeah. I just added one new word, and you could guess this change.
I have a question. Is it the same as three coloring problem?
No, now we require to use all colors.
Before, if it's not surjective.
Yes, before it was really just three coloring problem. Yes.
For this specific H.
Yeah.
For this specific H, yes, that's so. Okay, so what we know about graph homomorphism problems. In 1990, the complexity of this problem was described for all undirected graphs. Yeah? So if you have graphs without loops, and then the characterization is very simple. It turned out that the problem is NP-hard unless our graph is bipartite. Yeah, I forgot to say, but I hope it's really clear that any constraint satisfaction problem over a finite domain is in NP. Yeah, because if someone gave us a solution, we can easily check whether this is actually a solution. So every time I say NP hard, I mean NP complete today. Yeah. Okay, so for undirected graphs, in 1990, the problem was solved. And what is also interesting, in 1998, it was proved that this graph homomorphism problem is as general as CSP. Because for every constant language gamma, we can find a graph. Here it's a directed graph, such that CSP over gamma is polynomial equivalent to homomorphism over H. And yeah, from our result from 2017, we know the complexity of this problem for every directed graph H. Okay, what we know about the complexity of surjective homomorphism problem? It was described for partially reflexive forests. I don't want you to ask what it is. I hope I know, but still. In 2005, the complexity of this problem was described for all graphs of size 4, other than C4ref. What is C4ref? This is a very simple graph. It's just 4 cycles with all loops. So it's symmetric. It's 4 cycles with all loops. And it turned out that for this simple graph, the problem is not easy. And also it turned out that this problem was studied in graph theory, and there were many papers devoted to this specific graph because finding a surjective homomorphism to C4F is equivalent to some graph partitioning. So this was an important problem in graph theory, and this is really cool because for very concrete graph, we cannot decide whether this problem is easy or difficult. And in 2011, it was proved that this problem is NP-complete. And also, probably a bit later, the problem was solved for 6 cycle. So C6 is just 6 cycle without loops. And this is also amazing. Like for 6 cycle, it was an open problem for many years. What is the complexity of surjective graph homomorphism? Okay, I hope I advertised enough. Now I want to show you a very interesting example of surjective CSP. And this example is important because it contains the main idea of the proof of the main results of my today's talk. So if here you don't have any questions, then I will go on. Yeah?
Of course, we don't understand any of this. Have no idea how one can prove any of this, but it was not assumed, so we can just only wonder.
Yeah, yeah.
Up to now.
And actually, as for me, I also don't know how to prove this. But what I like is that I can draw this 4 cycle on a blackboard, and I can start thinking about this. I can give this problem to a student, and it's beautiful. Just you need to check whether you can find this mapping or not.
Yeah, but by the way, just a general question. So you say that it's interesting that we have an elementary problem, and for which we don't know whether it's NP-complete or not of this type. Mm-hmm. But is there any suspicion that it can be neither NP-complete nor solvable? Like, I don't know, graph isomorphism or one-way functions or something like this?
Yeah, good question. Like, till the last moment, most mathematicians believed in the conjecture I mentioned before, that surjective CSP and therefore surjective graph homomorphism problem is equivalent to CSP. And that's why it's always either tractable or NP-complete. But now, we don't know. But I will tell you about this more a bit later. Okay, so example which I really like, and that's how I started to think about this problem. Consider 2-element domain. So we have 2 elements, 0 and 1, or red and blue, whatever you prefer. And we have constraint language. This is just disjunction of equalities. For example, your instance can be like this. Yeah? And again, we can draw this instance on a picture as a graph. But this time, instead of edges, we have pairs of edges. So you see, we have pairs of edges corresponding to every constraint. Okay?
Yeah.
And an instance has a surjective solution if and only if we can choose one edge from every pair so that the obtained instance is not connected. So we need to choose one edge from every pair of edges so that the instance, the graph, wasn't connected. Okay, for example, this instance has a surjective solution because we can choose like this. So from every pair of edges, I chose one edge, And you can see that I have two components that are not connected. So this is a surjective solution. So what's your guess? What do you think about the complexity of this problem? Given pairs of edges, and you need to decide whether you can choose one from each.
The natural guess that it is in NP complete, but probably I'm wrong. It is
Since you asked, probably it's wrong.
Yeah.
Yes, yes, yes. So it's true. This problem is NP complete, NP hard, and I will show you the solution because it's really cool, in my opinion. So again, we have, yeah, I just erased what I don't need. Consider this instance. So I have these four constraints, which means that I have one variable in the bottom, one variable in the top, and I have many variables in the middle. Yeah.
And they should be connected to one of them, and this would be this dichotomy would be part of the reduction.
Yes, yes. So what we see on the picture, we see that every variable xi should be connected either to y or to z. And every variable in the middle should be connected either to y or to z. So what it means? It means that this graph is connected if and only if y and z are connected. Yeah, because all the other variables are definitely connected to one of them. So we just need to decide whether y and z are connected. And that's why we may assume that y is 0 and z is 1. Because if we have a surjective solution, then y and z should be different. And then without loss of generality, we may assume that 1 is 0 and 1 is 1. Okay? Yeah. So if we have a surjective solution, it's like this. But now imagine that we add this constraint like this. So this is actually a constraint like this, x1 equals x2 or x4 equals 1. Or we can draw this pink constraint, which is like this. And so we can add constraints of this form, equality and variable equals 1 or 0. And what this means? This means that if I consider any CSP over this language, but here I also use z equals 0, z equals 1. So I can express any CSP over this language as surjective CSP over my gamma. Yeah. And I hope it's clear how to express the first two constraints. Yeah. And with z equals 0 and z equals 1, it's also easy to say that z is to say that some variable is 0. I just identify this variable with the bottom variable with y. I just use equality relation.
But you mean that it's somehow obvious why the CSP is NP complete? Because it's kind of hard to understand what is really expressible here.
Yeah. You're right. Here I use that we know everything about CSP. And like this result.
Know everything.
And this result was obtained by Schaffer in 1975, I guess. So he characterized the complexity of CSP over any constraint language on two-element domain. And here we have just two-element domain. So we know that this problem is NP-hard. And we managed to reduce this problem to our surjective CSP. And so the idea is very simple and trivial. I just connect every variable in the middle to y or z. And this restriction is enough for us to express this CSP.
Yeah.
So I hope it's clear. So I proved that surjective CSP is NP complete. This surjective CSP.
No, it's not really clear in the sense that we probably cannot, if you remove your slides, probably we cannot say exactly what kind of gamma we have and what is where. But it seems that reduction is indeed nothing deeper than the reduction. It's just a standard type of reduction.
So the only idea is to choose two variables and connect every variable in the middle to like each of them by a constraint. This is the only idea. Everything else is really simple.
Maybe you can even take 3CNF and do something else and also make a reduction to avoid the reference to unknown.
Yeah. That's true. That's true. Yeah, you're right. But this time I just add this blue and green and pink constraints, and it's clear how they work. If I wanted to reduce from 3CNF, I would need something else.
Mm-hmm.
But yeah, in this case, the reduction would be from the problem you like and know. Okay. And now, no rainbow problem. What is no rainbow problem? This problem is one of the most famous surjective constraint satisfaction problem. So we are on three-element domain. We may look at this domain as it colors, red, blue, green. And our relation is like this. It contains all triples such that not all elements are different. That's why no rainbow. If all of them are different, then it's rainbow. Yeah, in our rainbow, it's just 3 colors.
So you ask for a coloring where all colors are used, but not at the specific triples. You have some triples when you should not use all 3 colors.
Yes.
You should use them somewhere else.
Yes, you're right. Correct.
A rainbow is probably a triple which has all 3 colors.
Yes, that's true. So so surjective CSP over R, I just repeat the definition of the surjective CSP here. So you get a conjunction of this R over some variables. We can repeat variables and so on. And I'm asking whether we have a surjective solution. So we need to use every color, but we are not allowed to use all 3 colors in one constraint. Okay, so this problem appeared in graph theory, and this problem studied for some time in graph theory. And if you know Manuel Badirsky, he offered €50 for the solution. It was more than 10 years ago. And as for me, I offered €500 for the solution. I even printed like 20 copies and put it in at the Moscow State University. I even printed a few copies for the High School of Economics. I'm not sure whether you did something with it. Anyway, so I really like this problem. Yeah. Okay. The question?
No, I just told that I used your copy, but I didn't succeed.
Thank you.
Do you know anything about the total sum of amounts of people offering? Because you say 2 people, at least 2 people offer something.
No, I don't know. Okay, so this problem was formulated many times as a concrete constraint satisfaction problem with unknown complexity. For example, there is talk by Hubi Chen where he formulates 3 concrete open problems, and this problem was one of them. Last time he made this talk, it was, I believe it was in March or something, so it was this year. Okay, what else is clear? It's clear that CSP over R is trivial because we can always take the solution 0, 0, 0, 0. If you consider surjective CSP over R with all constant relations, then it's NP complete. And this is clear just because we have a trivial reduction from CSP to surjective CSP. And we know that CSP over this language is NP complete. But also we can prove that surjective CSP over R with just 2 constants is NP complete. This is quite easy, but this is not obvious. Because here you cannot use reduction from CSP, because if you consider CSP over this language, CSP is also trivial. Because you can, if you can use only zeros and ones, and you succeed. Yeah, because if you use only zeros and ones, then all the constraints are satisfied. So again, if you consider CSP over this language, this CSP is trivial. Okay. And what I managed to prove, I proved that this problem is NP-hard. And this is the first main result of my talk. Okay, and I will try to explain you my proof. If you don't have any questions, I will go to the proof of the theorem.
But wait. Do we understand correctly that you received $50, €50 from Badirsky?
Yes.
Good.
No, actually, just at a good time to mention that we should congratulate it with getting a more serious prize at the next ICALP, I guess, or if I remember correctly. It's not only the $50.
In my opinion, it would be great to have a website like openproblems.com where everyone can donate any amount of money to any problem. And so instead of applying for grants, we could just solve problems and get some money.
And also somebody can get some money for positive solution and other amount for negative solution. So people may choose whatever they want to prove. Yeah.
Actually, that's true. Like in the original slides of Hubi, I can also show them. It was written that Manuel Badirsky offered 50 for any solution, and Hubi-Chen said that, okay, I will pay another 50 for positive solution. And by positive, he meant like polynomial, yeah.
Yeah.
Okay, so let's prove that this problem is NP-hard, or?
Yeah, no. So you say that you really hope to explain the proof completely. Then we switch from conference mode to undergraduate mode and start trying, or it's no hope to understand the details.
Okay, so the point is that I'm sure you will not be able to check every detail, but I'm pretty sure you will understand the idea, and in 1 hour you could repeat the proof by your own.
Okay, so we are still in the conference mood. Why not?
Actually, compared to your undergraduate mode, I thought that my mode is elementary. I don't know. Okay, so the idea of the proof. Consider this picture. Right now, I'm not explaining what I mean by edges here, but just look at these 3 pieces. Like between U and V, we have some number of variables. Between V and W, we have some number of variables. And between U and W, we have some number of variables. And
but at least this vertices are just variables who should be colored in one of 3 colors.
Yes, that's true.
Yeah. It's just not clear what are edges, but the variables are normal variables. Yeah.
Yes. And I want you to think about each piece as about the piece we had when we proved NP-hardness of disjunction of equalities. So when we considered disjunction of equalities, we had 1 vertex in the top, 1 vertex in the bottom, and some vertices in the middle. And now we have 3 pieces like this. Okay. And so what we want? We want V, U, and W to be all different elements, 0, 1, 2. We don't know how.
The restriction should guarantee that if 3 different elements exist, then they are necessarily UV and W are different.
Yes. So our dream is like this. We want to prove that if we have a surjective solution, so we used all colors, then V, U, and W should be of different colors. That's our dream. And I don't know how to achieve this, but assume that we managed to do this. So assume that it's 0, 1, and 2 actually.
Yeah.
Okay. Then I want all axes to be from 0, 1. And now I know how to achieve this. I just add these constraints. Okay. Then I want all y's to be from 1, 2. Then I add this constraint. And I want the I to be from 0, 2. And I add these constraints. Fine. What else I want? I want y's and z to be uniquely determined by x's. So I want yi to be xi plus 1 and zi to be just 2xi. And to achieve this, I add these constraints. Okay. And now imagine that.
So why this yi is xy plus 1 is represented like this? Can you?
Okay.
So you don't allow xi and yi to be 0 and 2 in any ordering.
Yes.
But why
Yes.
it doesn't mean.
But is it symmetric? I mean, y equals x plus 1 is not symmetric, but r is symmetric. How it can be?
Okay, let me think. So yeah, actually, you can just check that if these three constraints are satisfied, then this is the only option. Let's think about it. So assume that
you mean that you need z for so you don't try to implement one constraint. You just want for two constraints like this.
Yeah. So let's assume that xi is 0. So xi is 0,
Yeah.
and we know that y is from 1 to. Yes, which means that y should be
no.
1.
Why should not be 2?
So it should be 1 because y is from
yeah,
1 to.
yeah. Oh yeah.
So,
You have this additional thing. So
yes,
it's not
yes.
symmetric even before because it's yeah.
Yeah. Okay. So y should be 1. Okay. And then if y is 1, then what? Let's look at the last constraint. What we have? We have yi that I w. W is 2. Yi is 1.
So
Yeah?
it should be either 1 or 2, but it cannot be 2. It
So
cannot be 1, so it's 0.
Yes.
Okay, so you claim that we can check all the combination.
Yes.
And
Yes.
somehow mysteriously we have this.
Yes.
Okay.
And yes, and then the important part. Assume that we want to add this constraint. I hope you recognize this constraint. This is the same constraint we had for disjunction of equalities.
Yeah.
Okay.
And now y and z are somehow functions of x.
Yes.
Yeah.
And to achieve this, I just write this: xi, xj, yk. Why this is true? Because if xi equals xj, then this constraint definitely holds. If xi and xj are different, and yk is from the set 1, 2, then this just means that yk cannot be 2. Yeah? So yk is 1, which means that xk is 0. So by adding this constant, I just add this constant in the left-hand side.
But wait a bit. So your arithmetic, addition and multiplication is modular 3 or?
No, since they are just value, you see the values, xi is 0 and 1, and yi is 1, 2. So it's just normal addition. And
yeah, it's addition.
So
no, it's not normal addition. It's addition modular. Yes, it's normal addition. You're right.
Because they are just.
Thank you. Yes. And
so yeah.
Okay. So in the same way, we can add this constraint, just like this: yi, yj, xk. And you can check that if this constraint holds, then we have this condition on x's. So we learned how to add these constraints. We need to express CSP, and we know that this CSP is NP-hard. But we still don't know why V, U, and W are all different. Okay, so is it clear for now?
Not completely. Say it again. So you say that you reduce what to our problem?
Like you remember when I proved that disjunction of equalities is NP-hard, I took CSP over these two constraints, more or less. And I proved that and I found a reduction from this CSP to our surjective CSP. Here I want to do exactly the same. I want to find a reduction from this CSP to our surjective CSP. And that's how I add these constraints. Okay.
I'm sorry, but
still there's a mystical part
for
what is denoted by these edges.
Again?
So there are edges which you all in this graph, and you say that somehow they mystically guarantee that all three vertices V, U, and W are different. And this we are not assumed to understand how that's achieved.
Yes, actually that is the problem, because how I end the proof. After that, I just added all the constraints that are hold on any choices of X, Y, and Z. So I just added all of them that are always hold for any solution. And I was lucky enough, because after I added all of them, it turned out that any surjective solution is like this. For any surjective solution, V, U, and W are different. And the problem is that I don't know why it works. I just, so instead of explaining why it works, I am explaining how I get the proof. I just tried to express that CSP, and I learned how to express these constraints I need. And I just added all the constraint relation I can theoretically add. And I was lucky. So in the right-hand side.
Do you mean that you need to make only some finite amount of checks to see that it's true, because you have many variables, but the argument is showing that the three V, U, and W are all different.
Yes, yes.
It doesn't depend on the number of variables or what?
So the problem is that it assumes that you have a solution where V, U, and W are all zeros, but assumes that like 0 is red color, but assumes that blue and green color appear somewhere in X's and probably in Z's. Yeah.
Yeah.
And we use all these constraints in the bottom to prove that it's not possible.
Okay, but so say it again. So this edges between 0 and X and 1 and all these edges on the graph, they are just symbolic one. And what you say that you just add the constraints that you have. The edges do not mean any constraints specifically. Just
You may think, yes, like if you have an edge from 1 to x1 and from x1 to 0, you may look at this as a hyper edge, like because I have a constraint saying that 0, 1, and x1 are in R. So I have this constraint. But mostly it's just symbolic, because I just wanted to explain that the idea came from the disjunction of equalities, because I have 3 pieces and yeah, I express this CSP, the same CSP I expressed there.
okay, so probably we can, with some effort, we can believe you. And it should be checked somehow, but probably indeed it's not.
But so in my paper, it's just half a page proof. I just formally check. So assume that all of them are equal, like V, U, and W are equal, and some xi takes some value and y takes another value. Then I use this constraint, derive this. I use this constraint, derive this. But this is more like a formal proof. It's not like I know the idea behind this. I don't. And so that's what I can prove. I can prove that this CSP can be reduced to this surjective CSP.
Yeah.
And again, to express the relation z equals 0. So in my case, it's like xi equals 0, for example. To express this, I just identify xi, and the variable represents in 0 for me, and this is v. So if I identify xi and v, this means that xi is 0. So that's how I can express this constraint. Okay, and so that's how I can prove that this problem is NP complete.
NP complete.
Yeah, but the problem is still that I don't know why this construction works, because I just checked, it worked, and I published it. But I will tell you a bit more about this. So probably, yeah. Is it clear here? Like at least the idea, because what I want you to understand, I want you to be able to repeat the proof by yourself if someone will ask you, like, theoretically.
No, of course, there is also a question why this CSP isn't complete. But
we know this from 1975, so it's
okay,
not so.
1975. At that time, I existed, but didn't know anything. So.
But okay, actually, I can easily prove that this CSP is NP complete. For example, okay, so if you look at the first two constraints, x equals y or z equals 0, and x equals y or z equals 1.
Yeah.
Then using existential quantifier, we can compose them, and we can get something very similar. Let me think. Okay. Yeah, I need to write something.
Okay.
Okay. Yeah.
Okay.
Yeah.
That's part of yeah.
Okay. So let's go on.
Yeah.
So the idea is clear, and I don't want you to check that I did not lie to you. From the slide, it's better to take a paper and check it there. But anyway, the whole reduction is just one page, because I just say, okay, let's consider these constraints. And then I claim that there is a surjective solution if and only if this CSP has a solution. Okay, so the main results of my talk. I proved that no rainbow problem is NP-hard. And if you still remember this Hubitschian conjecture, that surjective CSP over gamma is polynomially equivalent to CSP over gamma with all constants. Then this result actually confirmed this Hubitschian conjecture. Because if we add all constants to R, then what we get is NP complete CSP.
So confirm doesn't mean to prove it. Just
no, it doesn't mean proved. It's confirmed.
It's consistent with this conjecture.
It's consistent with, yes.
Conjecture.
But that's what I thought confirmed. Confirm never means proof. It means that, yes, it's.
Oh, I'm not sure, but
it means doesn't refute.
Yeah.
Your result
no,
doesn't
if I
refute.
say that I confirm that somebody is a good person, it's something more strong that it's just consistent with my knowledge.
You found no evidence that he's
yeah,
bad.
I think it's a bit more strong. But anyway.
Yeah. And actually, I spent more than a month trying to prove this Hubitschian conjecture. And on Three-element domain, it's not so many really different constant languages. So I checked like 20 different cases, and in each of them, I managed to prove that this conjecture holds. And then I got stuck, and I found a counterexample, which was really terrible because it was such an amazing and simple conjecture. And now I have a counterexample. So what I found constraint language such that CSP over this surjective CSP over this language is easy, so it's in P. But CSP over this language with all constants is NP-hard. And this was really terrible because, yeah, now we don't have beautiful conjecture to be proved. And I plan to show you this example. I even plan to show you why this is a counterexample. Okay.
Yeah.
This is an example. So we have just one relation. This is 5-array relation. So columns are tuples. So this relation R holds on 0, 2, 2, 1, 0, on 0, 2, 1, 2, 1, and so on.
Yeah, so variables can have values 1, 0, and 2.
Yes.
And for tuple, we can require, for 5 variables, we can require that it's one of these combinations.
Yes, one of the columns. Yes, so just one simple relation. And I can prove that surjective CSP over R is tractable, so it can be solved in polynomial time. And it's known that CSP over R with all constants is NP-hard. And if you look at the right-hand side, you can see this R prime. What is R prime? R prime is just projection, is a projection of R onto the second, third, and fourth coordinates. You can see.
Yeah.
So I just considered projection. And the terrible thing is that surjective CSP over R prime is NP-hard. And this is terrible because R prime is easier than R. But for R prime, this problem is the problem is difficult, and for R it's easy. And
in which sense it's easier than R?
It's easier than R because it's it's just part of R. So actually, in this sense, every operation preserving R also preserves R prime, and this means that the complexity cannot be described in terms of polymorphisms. So usually, if we talk about CSP, we characterize complexity by operations preserving relations and preserving constraint language. And here it does not work because every operation preserving R also preserves the part of R, which is R prime. So in this sense, R prime should be easier, and it's not. And this is terrible, and now we don't know how to characterize the complexity in what terms, and so on.
Excuse me, just I can imagine that you can check every matrix of size 3 times 3, but how on earth anyone can write such a family of, I don't know, 6 relations, and each relation involves 5 variables? It's
just one relation. It's R is just one 5R relation.
Okay, but how anyone could come up with such an idea that we should study this specific ridiculous matrix?
As I said, I considered more than 20 or even 30 different cases, and in every case, I managed to prove that this Hube conjecture holds. And finally, I couldn't do this for some case, and so I started to build a counterexample, and finally I succeeded. So it's not that difficult example if you think about this for a week, for example.
In a week, I couldn't write such a matrix, I'm sure.
Yeah. So it's not like like this was my first matrix. It wasn't my first matrix I wrote. And yeah. Okay, so I hope I explained why this result was so sad, and because now we cannot use polymorphisms. And on the next slide, I will try to prove the first lemma. I will try to prove that surjective CSP over R is easy. So that's what I want to prove. Surjective CSP over R is can be solved in polynomial time. Okay, and what is the idea? Assume that I restrict the last variable of R to the set 1, 2. Just take all the columns with the last element 1 or 2. And so you can see that if I do this restriction, then my relation became easy. It's just like this. X1 equals 0. Here I use binary relation sigma. This sigma is just equality on 1, 2.
Yeah.
So if we restrict the fifth variable of R to 1, 2, then our relation became very simple. And if I restrict the last variable to 0, then again my relation became very simple, just like this. Okay, and now the algorithm. How I solve surjective CSP over R. So I have my instance, yeah, and you can see that the first variable of R takes only value 0. Yeah. The next 3 variables take only values 1 and 2. And the last takes all the values 0, 1, and 2. Okay? So we have our instance and assume that the fifth variable of one constraint appears as the second or as the first in some other constraint. In this case, we can use the reduction these 2 formulas. So we can simplify our instance by replacing R by something easier. And so every time I have this, every time the fifth variable of R is restricted, I simplify. And after I did all of this, I have two situations, two cases. Either I still have R. So it means that I still have some R, and the fifth variable of this R never appears as the first or as the second variable of some other R. And then I can easily get a surjective solution. I just send the variables with domain 0, 1, 2 to 2, variables with domain 1, 2 to 1, and variables with domain D to D. If you look at the relation R, you can see that I just send the first variable to 0, the next three variables to 1, and the last variable to 2. And I claim that if we simplified everything, then this is a solution. So the key idea is that if you look at the relation, then we have many tuples with 1, 1, 1. So almost always I can put 1, 1, 1 for the second, third, and fourth variable. So if we still have R, then we can easily get a surjective solution. If all R's disappeared, which means that we are left with just sigmas and unary relations. But sigmas and unary relations are simple. So then we can solve anything because this CSP is easy. We have a formula where we have just equalities and unary relations. And we need to check whether we have a surjective solution. Of course, we can do this in polynomial time. That's the algorithm. And that's the idea that R is complicated because if you consider projection of R onto the middle three variables, then this projection is complicated. But we are not allowed to use this projection if we are talking about surjective CSP. And it turned out that if we still have R, then we always have trivial solution, and that kills everything. If it's not clear, I will try to explain again.
No, of course, there is no hope we will understand the proof, but structure of the proof is more or less kind of tools used are more or less, because first you need to remember what is R, so you require that there are only either 0 or 2 colored vertices of color 2 among 3 variables, and somehow it's reflected in the fifth variable, and the first variable is 0. So okay.
Yeah. So like imagine you have an instance of surjective CSP over R, yeah, and imagine that every variable has the same domain in every constraint. Then obviously this reduction, what I define here, that I map variables with domain 0, 1, 2 to 2, I map variables with domain 1, 2 to 1, and I map variables with domain just D to D. This mapping definitely works and definitely gives us a surjective solution. Yeah, if you have an instance and you never substitute a variable with domain 0, for example, instead of the fifth variable having a domain 0, 1, 2. If we never do this, then it's clear why this reduction works, why this is always a solution. So the point is that if we still have R, then we have a trivial solution. And if we don't have R, then the instance is simple. Because R is split into something very simple, just equalities and unary relations.
Yeah, okay, so it's more or less believable that we see that there is no miracle at either. You can check this and it should work if it's okay.
Yeah. And I'm not sure, probably we can find Fourier relation, for example. For example, I'm not completely sure whether I need the first line, but the proof with the first line is just easier. So I decided that it's not so important. But three things in the middle is important, because if you have just binary relations, then the problem
Yeah,
cannot
okay,
be.
I think we should
Yeah,
leave
okay.
you at that point.
Yeah, okay. So I have just final slide, a summary of.
We don't hear you, by the way.
Can you hear me?
Hello.
Yes, yes,
No
we
sound.
can.
Yeah, we can. Yeah, Sasha, it's you
It's,
who are not here.
it's problem on Sasha's side.
Okay.
Still no sound.
Can you hear me now?
Yeah, we can hear you. It's Sasha. I think it's
I'm
Sasha.
asking Sasha whether he can.
Yeah, but
We cannot hear anything. Even we don't. We have a small indicator near your video.
Yeah,
see
we can
your-
hear
and the
we can
indicator
hear
doesn't
Dmitry,
tell
and
us
we
whether
even can hear
you
Sasha.
are saying anything. So probably your microphone is broken, or connection is broken, or something.
No,
it would be
Sasha, it's
nice
you.
If it all works.
Really interesting.
I think Sasha.
Maybe you should
Any one of us.
try to turn everything off and on, because now no chance.
Can you hear anybody?
Does anybody?
Yeah, everything is fine for me.
yeah, but Sasha cannot hear us.
Volodya, do you have
Unfortunately.
Telegram?
Sasha, I think he's not on Telegram, so
Okay.
we can hope we will look at the chat.
No.
And
Yeah, maybe you can kick Sasha off or do something brutal to him. Then he will understand that
yeah,
it's a problem.
I can mute him. I can
Don't
mute
do
Sasha.
this. If you kick him out,
Oh,
he
sorry,
will not be
sorry.
able to get
Yeah.
back.
I understand.
Yeah.
Sasha, is it okay?
Yeah. I'm sorry. It was my
Yeah.
problem, but strangely there is no signal. Okay.
Yeah, please next time check the chat, because we are it's
Yeah.
covered with messages to you.
Yeah. Sorry.
So, okay, I have just one final slide, a summary of what is known about surjective CSP. So the complexity was described for two-element domain. The complexity of surjective graph homomorphism problem was described for many graphs. You can see the survey of Badirsky, Kara, Martin. And at that point, all results were consistent with the chain conjecture. And in 2014, Hubi-Chen proved that if gamma has only essentially unary polymorphisms, then surjective CSP over gamma is NP-complete. So at that time, it was a hope that everything can be described in terms of polymorphisms. Yeah, then 2 months or, yeah, I guess 2 months ago, I proved that no rainbow problem is NP-hard. Then it was really recent result, just 3 weeks ago, I found this counterexample to Hubi conjecture. And just 1 week ago, Hubi-Chen published a paper on archive with some unification of hardness results. So he took my proof of the hardness result and managed to prove in the same way some other results, some other hardness result for surjective CSP. Like for me, his proof is still really complicated, because my proof has just 1 page and his proof has about 8 pages now. But still, it's some unification, and it's good because something good is happening. People are interested in this problem, new ideas appeared. And another good thing, yes, we can look at this as a good thing. We don't have a conjecture, so everything is widely open and the problem is cool. So go ahead and solve it. But first we need to find a conjecture, at least for 3-element domain, or at least for graph homomorphism problem, because even for graph homomorphism problem, we don't have a conjecture. And probably this Hubi conjecture holds for graph homomorphism problem. Like, as you see, my example is a bit artificial. It's 5-ary. And if you consider just binary relations, who knows, probably it holds. Okay, that's probably everything I wanted to tell you. Thank you. Any questions?
Thank you very much. Thank you very much.
So actually, I already asked this at some point. Maybe you can say now something. So is there any reason to believe that some of the problems could be intermediate? So neither NP-complete nor solvable? because now it seems that somehow there is a big mess, and you more or less find solvable parts, find unsolvable parts, and they somehow either is there a reason why it cannot do for forever, and everything can be classified?
So I would not bet money that there is something in the middle, because every time we could reduce surjective CSP to some CSP somehow. Like in all examples we have, we managed to do this reduction. So I believe we can always reduce to some CSP. And that's why I believe that for any language, surjective CSP is either tractable or NP-complete.
No, we can reduce, but maybe we can reduce to NP-complete something, and this doesn't mean that we are NP-complete. So it's not an...
No. Yes. What I wanted to say is that we can always reduce CSP, some CSP over some language. Yeah, like if the problem is difficult, yeah, we can reduce from some CSP. And so my point is that surjective CSP is very similar to CSP. And the only problem is to control, like if you look at the Hubble conjecture, it says that surjective CSP is equivalent to CSP over the same language with constants, yeah? And the problem is that how to get this constants. The problem is that is how to get this V, U, and W, taking these three different values from your domain. And if you have the three variables, it's not a problem to prove NP-Hardness. But probably this is not the answer, so I don't have an intuition. Because 2 weeks ago, I was completely sure that Hubble conjecture holds. I would bet money on this. Yeah. I'm glad I didn't.
Yeah. Also, another question is that so we know that one of the reasons why CSP are important is that there are some kind of mysterious for me results saying all this unique game conjecture, the hardness things. So what if for example you consider CSP in terms of as approximation problem, you want to have to check whether there is either all are satisfiable or less than 1/2 or something like this. Is there some kind of dichotomy result that either you have this for gap reduction or it's polynomial time decidable even in the approximate version?
Okay, to be honest, I know nothing about approximate surjective CSP. I never thought about this.
No, it's this unique game conjecture. It's so strange and so easy that it should be advertised. You have a graph.
Yeah, I know.
And you have a one-to-one correspondence, and you want to find as many of them as possible to be true. And still it's so it's an example when the difference between full solution and approximate solution is maximal. So it seems that if there is so clear theory of dichotomy for exact CSP, maybe something is known about approximate CSPs.
Yeah, something is known, and I know that a lot of people who studied CSP, now they actually moved to unique game conjecture. They started to think about this problem and started to think about approximation, counting, and so on, different variants of CSP. But till now,
there are some results.
Succeed.
They start to think, but do they achieve some kind of results about approximation CSP for general type of CSP, not specifically?
Yeah, they have some results, some of them, but I'm not aware of some strong results. And I never, okay. So I never thought seriously about approximate CSP. I've heard a lot of talks, but I never thought about this seriously. I know about Unix game conjecture. I know that it's still open, and I know that people doing CSP or who studied CSP 2 or 3 years ago, now they move to Unix game conjecture and they move to promise CSP, which is another cool variant of CSP, if you know what it is.
And can you say what it is? What is
so
the
promise CSP, for example, if you consider a graph 3 coloring, yeah. So imagine you are given a graph, and I promise you that this graph can be colored into 3 colors. But I ask you to color it into 100 colors. Can you do this in polynomial time?
Oh, yeah. This is.
Or we may consider decision variant. Like I give you a graph, and I promise you that either it can be colored into, I don't know, 1 million color, either it can be colored into 3 colors, or it cannot be colored even in 1 million colors. So I gave you this huge gap. Would it be easier for you to solve this problem than just usual 3 coloring?
Yeah, it's just gap reduction.
Yeah. And but you can formulate this in general. Like if you consider CSP, you have a constraint language. But instead of imagine that in this constraint language you have pairs of relations. Pairs of relations of the same arity. One is weak, one is strong. Yeah. And so I give you an instance or conjunction of these relations, and I'm asking you whether the strong part holds or even weak doesn't hold. So I give you a promise, and the question is whether this problem is easy after that. So this is a very general question, and this is a really cool question because what they found and what they discovered now is really beautiful. So now they understand even CSP better, because now they know how to reduce CSP to some minor conditions. Probably you don't know what minor condition is.
No.
Okay, but I can give you a talk on this topic sometime, because what they discovered about not surjective CSP, promise CSP is really beautiful.
Any more questions? Okay, let's thank a speaker for a very nice talk. Somehow, I don't know, there are reactions here, we can use reactions.
Yeah.
Okay, thank you very much.
Goodbye, everybody.
Okay, do we have some plans for next week or for...
Not really, not right now.
Not yet, yeah, okay.